Okay, so we're talking about language, right? Language in general, we use it to communicate, and hopefully whoever we're talking to understands what we're trying to say. In math, I like to think of it as a communication between ideas. It does this by getting rid of things we don't need and focusing on important things. So for example, this sentence, I did put a picture on it, the dog went home. We all understand this, we don't have the context for it. We don't know what the dog is, or how it went home, or it's home, or anything like that, right? But we have an understanding of this, which is sometimes what we do in math. So like for the word dog, for example, you have an idea of what dog is, right? In your mind, there's a category of dogs, and that's what you pictured, even though I didn't specify what the dog was. So these are all dogs, memes, but what about this, right? Because although you have an idea of what the dog is, when I ask you to define it thoroughly so that it's precise, so I can point out to anything and then you can tell me if it's a dog or not, our definitions aren't usually very clear, right? So this one, it could be a dog, some might interpret it, but some might not. So in math, what we do is we define things very well. So I will call these dudes, okay? They are four-legged creatures with tails. Anything that's not four-legged, even if it might be a dog that was amputated, so it now has 3 legs, is not a dude, okay? So we do something similar with went home, and we have the dude went home. In math, we like to use small letters to mean that a particular dog from do, and then it went home, wherever that home is exactly. So it's very well defined, right? And once we have this, this is but going back to that, that means this is a mathematical expression. There is meaning behind it. Okay, that's what I wanted from this slide. Is even though it looks complicated and all of that, it is in a way a sentence. So going back to do, once we have it well defined in math, then we can start playing around with it. Is it possible that Pum went dog or Dug went dog? I don't know. I'll get to that in the next slide, but these are things that we can talk about. We can maybe change definitions. And as I said, I have no idea. Well, one of the reasons is because I did define it well enough. I just gave categories, but I didn't talk about interactions and things like that. So I have no clue, right? But on the next slide, hopefully there's a bit of a better example. This is Königsberg. There are 7 bridges here. So there's an island in the middle, landmass there, and over here. It's separated by a river. And this is a Königsberg 7 bridges problem presented by Euler. And he basically asked if it's possible to cross all 7 bridges without going through any twice, right? And so he simplified it. This is what I'm talking about. We get rid of things we don't need. We don't really care about the width, the length of the bridges. So we have the center landmass. It goes to the upper and lower landmasses. And then the one on the right, there's all bridges connected to them. And it turns out that it's not possible, right? And it's what started graph theory, essentially. Now, graph theory, you might not have heard of it, but it's actually pretty much everywhere. I was looking it up, and it's used apparently in linguistics also. Anything with lines and connections, traffic, networking, it's all over there. So I've drawn this. You have 6 points there connected by colored lines. Now, this is in Ramsey theory, Ramsey numbers. And it turns out that if you use 2 colors, right, no matter how you color those lines, it turns out that you'll always be able to find 3 points that are all connected by the same colored lines. So what happens is, that means if you can take, for example, 6 animals, you can find, if you define a property, like does it have 4 legs, you will be able to find 3 of them that either have 4 legs or do not have 4 legs. So for any 6 things that you take, you can basically do this. So any 6 things. Now the important thing is, we're only using 2 colors. So it's like it has that property or they don't have that property. So if you want later on, you can get a group of you and say, for example, see if you can find the 3 of you that are all above a certain age or below that age. So you can gather yourselves. And math here is, essentially there are, I feel like 4 or 3 parts, I can't remember. First one is definitions. It's like what we did with do. We defined it, that's it. Now sometimes we can be flexible with this. Sometimes it turns out that our definition isn't very good, so we can modify it. Now the other thing is we have rules. Sometimes they're called, usually they're called axioms, and this is basically our sort of rules of interactions. As I said before, I didn't quite define it well enough for the dog went home. But,
Dog went home. Well, that was a fluctuation, so let's just wait for the PowerPoint to come back. Can you turn it on? The yellow light. Thank you. Whoa, you can rest for a while. Okay.
Is there a mask behind that white?
There you go. Okay.
So aside from those, once you have those set, then you can start playing around and exploring, right? As I showed you earlier, what are things that are allowed, what aren't, things of curiosity, and that's what a lot of math, that's where the brunt of maths is. It's just that that's not what's usually taught, because before you can get to this, you need to know your definitions and all of that. And once you play around, discover things, you share it. So mathematicians, we do research together, things like that, because although some mathematicians work alone, eventually they will share what they've learned, what they've discovered, and that's how we basically spread the knowledge. And my last slide, the smiley face, I like smiling. And I really enjoy math. The truth is, I actually like psychology, but the way the mathematical approach really helps define things, because as you all know, the mind is quite complex and very subjective.
All right.